Imagine standing on the rim of the Grand Canyon, staring down into nearly 2 billion years of Earth's history, layer after silent layer of stone. How could anyone possibly read a timeline this massive? How do we know the age of a dinosaur bone or whether trilobites came before T-Rex? What does it actually mean to say 65 million years ago? Welcome to Physical Geology 001A at West Valley College. I'm your professor Farida Bakshi Musa, and today we're going to unlock one of geology's deepest secrets: how we measure geologic time. Whether you're a rock enthusiast or just here to earn your science credit, you're about to see our planet and human history in a whole new way. So let's jump in. Back in the 1700s, a self-taught English surveyor named William Smith was busy mapping canals. While everyone else saw only rocks, Smith noticed something unusual. The deeper layers had different fossils than those above them. And this is key. The pattern was the same wherever he looked. He realized that specific types of fossils always showed up in the same order as you went down into the earth. This was the birth of the principle of faunal succession, and it let Smith do something no one else had ever done: build the first geologic time map of England and Wales in 1850. He and others after him gave us many of the time period names we still use: Cambrian, Devonian, Jurassic. They didn't know the actual ages, they just knew the order, which rocks and their fossils came before or after each other. Now we use an internationally agreed upon geologic time scale. At the grandest scale, Earth's story is divided into 4 eons: the Hadean, when our planet first formed; the Archean, when the first oceans and life appeared; the Proterozoic, when oxygen rose and life became more complex; and the Phanerozoic, which is the eon of visible life, the time of trilobites and dinosaurs and us. The Phanerozoic alone covers more than 500 million years, and it splits into 3 eras: the Paleozoic, the Mesozoic, and the Cenozoic. Each era is broken into periods. Think of Cambrian or Jurassic, and each period into epochs. Right now, we're living in the Holocene epoch, which only began about 11,700 years ago, just after the last big ice sheets melted back. But how did we figure out which layer was oldest or youngest long before we had actual dates? Geologists built rules for relative dating. The most basic idea is superposition. If nothing disturbs them, younger layers stack on top of older ones. So this will be the youngest layer, this will be the oldest, the one below. Layers are usually deposited flat, unless something like tectonic stilts or folds them. Anything like a dike that cuts across layers must be younger than the rocks it slices through. And little fragments of one rock stuck inside the other, the fragment must have come first. That means it's older than the rock in which it's stuck. And unconformities, giant gaps in the record, show where time vanished from the rocks, pages torn from Earth's history by erosion. James Hutton called one famous unconformity in Scotland the abyss of time, because it revealed a span so enormous no human record could begin to describe it. Fossils, though, are what really brought the time scale of life. Some creatures, for instance trilobites, appear only in the Paleozoic. Others, like ammonites, are classic markers for the Mesozoic. Woolly mammoths, those are signs you're in the Ice Age. And the sudden disappearance of fossils is just as telling. When dinosaurs vanished at the end of the Cretaceous, the extinction drew a line across the rocks. Below, dinosaurs everywhere; above, gone for good. That's how geologists mark boundaries between eras and periods. But there was one thing missing: numbers. The geologic time scale originally was just a sequence, like a photo album with no dates. So when exactly did the Cambrian start? How long ago was the asteroid that wiped out the dinosaurs? Those answers came in the 20th century with a scientific breakthrough: radioactive decay. Atoms like uranium, potassium, and carbon are actually tiny clocks ticking away at known rates called half-lives. When minerals form in a molten rock, they start counting by measuring how much of the radioactive parent is left and how much daughter product has built up. Geologists can actually date when the rock formed. Let me show you how this works. Imagine you're holding a piece of granite. Inside those sparkly pink potassium feldspars, a few of the potassium ions are unstable. They change into argon gas over time. When that feldspar crystal formed, it was argon free. As years, millions of them pass, argon builds up inside. If we take that crystal, crush it, and measure the ratio of potassium to argon, we can calculate exactly how long ago the granite froze from magma. This is potassium argon KAR dating. Zircon crystals, on the other hand, are perfect time capsules for uranium lead dating. They used to find some of Earth's oldest rocks, more than 4 billion years old. Then there's rubidium, strontium for even older rocks, and radiocarbon, carbon-14 for anything young, organic, and up to about 60,000 years old. That last one is especially useful for archaeological sites and the most recent parts of our climate record. Isotopic dating doesn't usually work directly on sedimentary rocks. Why? Because those rocks are bits and pieces recycled from even older materials, and each grain might have started the clock at a different time. Instead, we bracket the ages by dating nearby volcanic layers or by dating fossils if we're lucky. For example, radiocarbon dating has helped us trace the retreat of ice sheets in Western Canada. By dating wood inside glacial layers, we know ice was at Campbell River 35,000 years ago, and Vancouver about 25,000 years ago, and had reached Victoria by 22,000 years ago. And when we extract tiny zircons from sandstones and date them, we are not learning the age of the sandstone itself, but we are learning about where its grains came from, which mountains, which ancient rocks, which continents. Every grain can tell a different origin story. But isotopes are just one way geologists check Earth's clock. Tree ring dating, dendrochronology, can take us back about 14,000 years by counting the patterns in ancient wood. Earth's magnetic field, which reverses every so often, leaves patterns like barcodes in newly formed seafloor. Imagine when basalt comes out of the seafloor, where the plates are moving away from each other, divergent plate boundaries, and when they melt, when the melt solidifies, the iron in the basalt, it aligns in the direction of the existing magnetic field. So it leaves patterns and barcodes, like literal stamps in the newly formed seafloor. Together, these clues help us reconstruct events large and small. Alright, here's the part where things get philosophical. Facts about time are one thing. Knowing that the Mesozoic started 252 million years ago, or that the last ice age ended 11,700 years ago. But truly grasping these numbers is hard. Our lives last maybe 80 years. Even the span of all of written human history is about 6,000 years. A mere speck on Earth's timeline. Let's put it in perspective. Continents move a few centimeters a year, the speed your fingernails grow. Yet give them hundreds of millions of years and oceans form and close. Sediments may accumulate less than a millimeter per year. Blink and decades pass. But over millions of years, these tiny annual increments build rock layers kilometers thick and carve canyons like the one we started with, the Grand Canyon. And climate? Earth cooled 12 degrees from the steamy Eocene 50 million years ago to today. But that cooling averaged only 0.000024 degrees per century. Today, in just the last 100 years, humans have warmed the planet by over a degree. That's almost 50,000 times faster than the most dramatic natural shifts in Earth's geologic past. Maybe the best way to visualize it is to shrink all Earth's history into 1 year. This will be fun. Earth forms January 1st. Life shows up late March. Multi-celled animals mid-November. The Cambrian explosion just before Thanksgiving. Dinosaurs show up on 13 December and are gone by December 26th. The last glaciation, 6:30 p.m. on December 31st. Humans in Western North America, 11:59 p.m. All of recorded history, the last 2 seconds before midnight. So we are quite literally geologic newborns. We are the blink at midnight. And one final thing. People often call everything before written records 6,000 years ago prehistoric. Dinosaurs, mammoths, early humans. But that's a human-centric term. From a geologic perspective, to call a dinosaur prehistoric is like saying San Francisco is beyond the city limits of San Jose. It's true but misses the point. Geology stretches our understanding about mere human history and lets us see the grand sweep of time itself. So, to summarize, William Smith's discovery of fossil succession gave us the first timescale. Relative dating put rock layers in order. Fossils reveal the sequence of life and extinction. Isotopic clocks gave us the numbers: potassium, argon, uranium, lead, radiocarbon. We use three rings and Earth's magnetic reversals too. But the deepest lesson is to train yourself to see time differently, to understand that the slowest processes, given enough time, can reshape mountains, earth, oceans, and even the climate. The rocks that are at your feet, they're not just stone, they're a book 4.5 billion pages thick. That's the age of the earth. And we students of geology get the privilege of learning to read it. So thank you for joining me in this lecture, and if you have any questions, please come for my office hours on Friday or send me a message. If you have questions, I'll arrange another office hour link, and do your assignments on time, and I will see you in the next video.